My name is Henry Snow. I'm VP of Infrastructure for the Nielsen Marketing Cloud, and I'm here to talk about how we handle operations. I've been the primary Aerospike admin for our group probably for the last 4 years or so, and I've been working with the group for about 4.5 or so. So let's dive into it. I'm going to do a quick overview of what the Nielsen Marketing Cloud is, go through our tech stack a little bit, talk about how we're actually implementing Aerospike, and then dive into some, let's call them hurdles, the things that made us think a little bit more before we just did something as we went through operations. So the Nielsen Marketing Cloud, we are in advertising technology. We are not part of the bid stream, so we do not do any actual ad serving. So you got a fantastic intro to ad tech yesterday from the trade desk. We sit upstream of that. So our job is to provide the best possible data to marketers so that they can actually activate these devices or users on the platforms that serve advertisements so that the best return on investment can be gleaned from the ads that are being served. So we started as a company called Xlate, which was founded probably about, 9 years ago at this point. We were purchased about 4 years ago by Nielsen, and so we're a digital data group inside of Nielsen. Our main focus, as I said, is data enrichment. We really want to take either the data that a company provides us, be able to enhance that data and kind of make decisions based off of data science models to enhance that data, and then deliver that to platforms. This is a quick screenshot from the Marketing Cloud platform. It's showing off insights that can be gleaned about a segment of the population that is interested in home improvement. So this home improvement segment is made up of about, just says it right up here, 337 million users, and they seem to be very interested in cruise ships as well as theme parks. So with this in mind, if someone who's marketing, let's say a cruise, wants to get the best return on investment of the ads they're serving, they might target home improvement users to do this. Cool. So let's go through a little bit of our high-level architecture. We can break our software stack down into 3 sort of distinct parts. The front end, which is where we ingest all of our data. This is where Eraspike sits, and this is where we'll be kind of focusing the most part of this presentation on. The back end, which is where we aggregate all the data that we collect into various either databases or data lakes. And then finally, the application stacks, which are what actual clients interface with so that they can interact with our data or actually use our data and export it from the system. To kind of give you a quick summary of how this all works, coming in on the left there, we have HTTPS calls. Most of our traffic is online calls coming into our system to web servers. It's geographically balanced and distributed across our various facilities using an NS1 DNS provider. Inside the front-end stack, I'll get into this a little bit more on the next slide, but we can process the data, store the history of the user that we suddenly are seeing, as well as do some modeling. Finally, we can ship that data via Kafka and uReplicator over to our backend cluster, where we actually will do some MapReduce ETL processes on it, store it inside those databases, and make it available to the applications. We have currently 8 facilities globally. We have 3 in the United States, 1 here in California, Texas, New York. We have 2 in the EU, which is Amsterdam and Frankfurt, and then we have 3 more facilities which were recently launched within the last year and a half in APAC. So we have Hong Kong, Tokyo, and Sydney, Australia, which is our newest child. All of these facilities are sitting inside of Packet Bare Metal Cloud. We choose to host with Packet for a variety of reasons. Specifically, we can influence the hardware that we're using much more than we can with, let's say, Amazon or GCP. We try very hard to have fantastic performance with our system, and being able to influence the hardware and the device storage choices with Packet is fantastic. We also have a decent amount of control over the network latency from rack to rack, where if you are operating in, let's say, Amazon and you're using multiple AZs, you might have 9 milliseconds or so, plus or minus, between AZs, which can kind of be a game changer if you're trying to do sub-millisecond transactions. Cool. Let's dive into one of these facilities. In terms of components that interact with Aerospike, we have two main ones, Expresso and Extreme. Expresso is our front-end web application server. It's responsible for processing about 5 billion transactions every day, distributed across the facilities, of course. It's responsible for completing any sort of HTTP call that's coming into our system in less than about 250 milliseconds. The 250 milliseconds includes DNS lookups, networking to our facilities, the actual work that the application server does, all of the modeling that we might do on the Extreme servers, all the lookups, the reads, writes from Aerospike, all that jazz, and we need to return it back to the client. This is different from some of the actual ad serving platforms where they might have 10 milliseconds or 100 milliseconds or so. So we get a little bit more leeway, but still 250 milliseconds is pretty short. The Extreme servers, I said, there are modeling servers, so they're responsible for scoring and segmenting the devices that we're seeing based off of either models that were pre-built or online learning models which are responsible for training themselves given a certain set of circumstances. Lastly, we have Aerospike down here at the bottom. Aerospike is our device history storage. So every time we see an object, or sorry, every time we see a device, we need to know, have we seen this device before? What happened when we saw it before? And we need to store any new information that we've gleaned from this current transaction. Lastly, we use Aerospike to provide cross data center replication. This means that any of our 2 or 3 facilities per region share the same data to the best of our ability to with XDR. So that if a user decides to get on an airplane and go across the country to California, let's say, they'll have the same data available in California as they did in New York, with still a short amount of latency to actually reach our web servers. This also allows us to do failover, where if we have an issue or we want to do a major upgrade in one facility or another, we're able to take that facility completely offline, have 1 or 2 more available for us, and they have all the data available to them fully. Cool. Okay, what do we store in Aerospike? We can break our we have 2 namespaces in Aerospike. We have our users and we have our lookup namespace. So users are really devices. So these are either a cookied ID, so a randomly generated identifier that is stored in a cookie attached to your web browser or mobile phone, or it might be a mobile ID, so like an Android app ID or an iPhone, whatever the ID number is for iPhones. So those are our device users. We just call them users. The users object store some general variables such as when did we last see them, where were they in the world when we saw them, how many times have we seen them, maybe what time zone they're in, just general information. We store segment history, so when we saw this device last, how did we say this device was associated with someone who was male, who was maybe 25 to 30, who was interested in phishing? So this might all be stored in the user object. We also need to know who gave us that data. So what provider? Was it first party? So did we acquire it through a tag that we put on someone's website, or is it a third party publisher that gave us this data? We also need to know the delivery history. So this is who bought the data from us. Things that are pretty important in ad tech is not overselling data to someone. So basically, you might not want to update a platform more than once every 30 days or something along those lines with this device ID and the segment history. So we need to know who we sold the data to. We also store household IDs. So a household might be, let's say you have your phone, your laptop, and your second laptop, who knows, or you have other people in your household that have computers as well. We might group these all together in a way so that we can actually interact with them as kind of one object. If someone's watching, let's say, like over-the-top like linear television, so what you like a cable box, we might be able to say like these 6 devices were all sitting in the household. They might be interested in this program. Maybe we add them to that. Our ID mapping, so this is our lookup namespace. So these are internal to external mappings. So it might be a publisher has a different ID for representing this device. We have our own representation of this device, let's have a way to connect the dots between the two. We also store hashed IPs. IPs are considered PII, and we don't store any PII, so we store hashed IPs instead. So we have a way of mapping that from an IP address to a user. We might also store household IDs as well. Object storage. So in terms of what we actually do inside the namespaces, our namespaces are single bin, so that means that we're not taking advantage of the Eraspec feature that allows you to have, I don't know, individual, let's call them columns, bins, inside of Aerospike, but we have one area where we do all our reads and writes from. The reason for that is because we heavily compress all the data that goes in and out of these fields, or the field, as a binary blob. And we were able to drastically reduce the amount of storage footprint we actually need by doing pre-compression. At this point, Aerospike's released compression, so that's pretty cool, so we'll have to check that out. Maps data types are pretty useful if you want to interact with an object, but not actually either retrieve the entire object from Aerospike, or you don't want to have to do a write that will cause an entire object rewrite. Cool. Talking about our actual clusters, our US clusters are definitely much larger than the rest of the world. Our US clusters are made up of 12 nodes and have about 140 terabytes of used storage, 14 billion objects spread across the nodes, and we see on average about 100K read TPS and 75K write TPS. This is on average. It might spike up to almost double that. We also see about a continuous average of about 15 gigabits a second of XDR traffic, so it's a pretty high volume in terms of replication. The EU clusters are a little bit smaller than that, but the ratios remain approximately the same. I wanted to talk a little bit about how we do configuration deployment. I'm touching on this in a pretty short fashion. We use Ansible. Ansible is pretty much our configuration deployment tool of choice. We have been using it on, I would say, all of our systems for as long as I've worked at the company. It's a fantastic tool that allows you to write pre-scripted playbooks, basically repeatable roles that you combine together to deploy your server out. This is on the on the right-hand side for you guys, a quick example of a YAML file that would allow you to deploy aerospike.conf and test if the Eraspike server is actually running. If so, and you chose to restart the server. This allows us to scriptably do version upgrades. You're able to quiesce a node, make it drop out of the cluster gracefully, upgrade the version, bring it back in, wait for it to rejoin, and then move on to the next one super simply. Ginger templating is awesome as well. It allows us to template out all the IP information about connecting the dots between the meshes for node discovery, as well as XDR IP address discovery for the remote data centers. Cool. Monitoring. We have recently switched to use Prometheus to do a significant amount of our monitoring inside of the NMC. We had been using Zabbix for many years. Zabbix is kind of tried and true. It's a neat application, but what we found was that with dynamic metrics, with dynamic hosts and dynamic metrics, it's very hard to add and remove those. Also doing application level metrics is basically custom script writing, or you happen to find some person's script on the internet and you chose to run it, which isn't necessarily the best thing. Prometheus allows you to do time series-based metric collection using dimensional data. You're able to have labels associated with a specific metric, so you're able to dive deeply, or as deep as you would like, into the metrics that are available. You also get the advantage of independent clusters per region, which allows you to, if you're having a problem with metric collection for whatever reason, you're able to isolate this. You're also able to handle alert management through these. Prometheus uses something called exporters to make the data available. Prometheus scrapes metrics, so whenever you are making metrics available, you're producing them in a plain text HTTP server-based format, similar to what's here at the bottom. And the Prometheus cluster will come along and scrape this data and ingest it. There are I would say hundreds of exporters available. Prometheus's website has a ton available on them. Aerospike's is literally at the top. I guess that's what you get for naming a company beginning with A. But yeah, it's right up there, and it's pretty reliable. Now, I said that all of the metrics are, or all the Prometheus clusters are distributed and separate. We want to have one way of being able to say, what are all my servers doing? I don't want to jump between interfaces to go figure out what metrics look like. There's a fantastic open source product called Panos, which is responsible for bringing all of your Prometheus cluster metrics together. It's really hard to Google for Thanos right now and not get spoilers. I haven't watched the movie yet, so I've been like on edge. But it provides a Prometheus completely compatible API. You can integrate it into Grafana and pull out metrics or pull out displays like this in Grafana panels. The really cool thing it also allows is metric downsampling. So if you have, I don't know, information or metrics that you're interested in at a high resolution for the first 30 days or so, but after that you kind of only care about like 5-minute resolution or 1-hour resolution, you can configure automatic downsampling, so it will crawl through that and reduce the storage need. Storage also is S3 or object store, so you're able to basically store an infinite amount of metrics, assuming you can pay your bills. But it's pretty awesome. And we've been using it for about, I'll call it 5 months at this point, beginning of the year, and it's been very successful. Cool. I wanted to dive into a couple operational scenarios that, as I said, kind of made us think a little bit as we went through them. The first one is adding a second EU facility. Prior to 2017, we had 4 facilities globally. We had our 3 US facilities and 1 in Amsterdam. The US facilities use XDR to replicate all of their data between them using like a star replication pattern. They all send to each other. And our Amsterdam facility was responsible for just sending data continuously to our New Jersey facility, where we had the extra namespaces for our EU data available there. It worked pretty well for a while, but there are a couple issues. One is you have a pretty limited link between, or we were paying for a limited link between the 2 facilities. You had about 94 milliseconds of latency. For reference, New Jersey to California is typically about in the 70s, let's call it, and then to Dallas is about 34, I believe, from New Jersey. So this was a pretty significant increase in latency for any sort of outbound XDR from New Jersey. We're also treating it as just a failover. So if we had any problems in our Amsterdam facility, we'd activate our New Jersey facility for EU traffic via DNS. But there are a couple problems with this. One is you have this undersea cable, which at that point in time, they kept on getting cut. And while you have redundant paths, in 2017, it was super popular, I guess, to like drop things on cables. So when your failover is across the ocean and these cable things are happening, if you have problems in Amsterdam at the same time, your failover is kind of, I don't know, hard to come by, or it's not convenient, I'll put it that way. So that's definitely a problem. Currently, as of today, we still only have 1 outbound XDR queue. So if your New Jersey facility needs to replicate data to California, Texas, and Amsterdam, and your Amsterdam link is going super slow, and you have 1 object or 10 objects or whatever that need to be replicated over that link, it delays the entire US-based replication as well. This is changing in very soon Aerospike release, I believe, which is awesome. Lastly, we had to store not too much data, but we had to, at this point in time, we had individual disks for the EU data, and we had to store all of that. We had to have an extra 2 disks or 3 disks per Aerospike node in New Jersey as well, which was kind of, I don't know, silly. So Frankfurt. Frankfurt came along, and we were speccing out data center facilities. We decided to go with Packet as a cloud vendor for this, which was a change for us. We also had been keeping our eye on NVMe devices, and we were upgrading to the Micron 9200s. we had never done cross-cloud networking before. Our backend capacity was always privately provided by our hosting provider. Now we have 2 hosting providers. They don't necessarily want to provide a private link without breaking the bank between the 2, so we have to figure that out. We also have to do this live, so we have 5 terabytes of objects, and we need to replicate them around. Cool. I was going to touch on WireGuard for a moment because I think it's an awesome project. WireGuard is an open source in-kernel VPN. If you have ever configured an IPsec VPN and you live to tell the tale, you know how much trouble they can cause, especially if you have 2 different vendors on either side that don't call everything the same thing, or even just in general. Right down here on the side, this is literally all the WireGuard config for setting up a secure tunnel between 2 facilities. There's no more config than this. I'll let that speak for itself. These are not the actual keys, but those are from the WireGuard example online. So I said it was high performance. So you're able to do 2 gigabits a second from node to node over top of it. I think that's a pretty big win. We had about 1 before this, so that met our needs. The one, I don't want to call it the downside, but it's the downside. There's no out-of-the-box high availability, so if you can't necessarily have 2 WireGuard tunnels up that automatically load balance your traffic over top of it, but I don't know, scripting is possible. We've implemented that recently, but it's an awesome project. Cool. So how did we actually end up doing it? So we've kind of touched on configuring the network between the 2 sites. It's actually 3 sites because we needed to have Frankfurt, Amsterdam, and New Jersey all in sync at the same time. If during this process we had an issue and we needed to shift out of Amsterdam, writes would suddenly be occurring in New Jersey. And if we didn't bring those writes over to Frankfurt, we'd be missing out on data. So we have kind of another new star replication pattern configured here, and we got that up and running. XDR configuration is pretty dynamic. All except for 1 step you can configure on the fly with live clusters. The 1 step you need to do ahead of time, which again I believe is changing soon, but is you need to kind of set up an empty template for the remote facilities. Besides that, you can add and remove nodes based off of their IP address or the individual namespaces completely dynamically through ASInfo. So that's a pretty big plus. That gets the data flowing, so any new writes are able to be replicated at that point. There's a lot of history, though. I think we see about 1/3 of the namespaces turnover every day or 2. So what I mean by when I say that is that 1/3 of the objects in the namespace get written to every couple days. That covers most of it, but there are definitely some stragglers. We have a TTL of about 40 days, so that means we'd either have to wait 40 days for XDR to finish, we'd have to go through and touch every single object in the namespace, basically do a write on it, and like a dummy write where nothing really happens, but that would trigger XDR. Or we can use AS Backup and AS Restore. So these are the backup and restore tools that come with Aerospike. The restore tool has an awesome feature, which is the unique flag. Basically what that says is that when you're doing the restore, don't overwrite any objects that already exist in this namespace. With that, we're assuming that XDR started before the restore started or before the backup was taken. That means that any objects that are already in Frankfurt when we do the restore are newer than whatever's in the backup. So we can actually do that live. So we were running AS Backup and Restore on a application node sitting in Frankfurt across the tunnel to Amsterdam, running the backup locally, and then as the data streamed in, we were importing it and restoring it to the cluster live. That works with pretty low latency links. If you have high latency links, I recommend uploading it to S3 or something along those lines and getting around that. Lastly, we update the DNS GSLB to bring the facility online, check and make sure everything's working. Of course it is. And then remove New Jersey from the star. That's kind of our migration steps for this, and it worked very successfully, I would say. Cool. The next scenario is, I touched on using microns before. In around 2017, 2018, we decided to refresh all of our servers in the US. We were using Intel SSDs, like traditional SSDs, and NVMEs were the new hot thing, so we were speccing them out and seeing what would work for us. The most important thing to take out of this is testing your drives before you buy them. Aerospike provides a certification tool, the ACT tool, which allows you to stress test your drives as close to with fake data. It builds randomly generated fake data for you, and it allows you to stress test your drives over time to make sure that they'll meet the TPS goals that you have in mind. It allows you to do a couple things. One is you choose your TPS that you actually want to try out, and you're also able to adjust your object size. So, for example, I think, I shouldn't quote myself on this, but I think it's approximately 17 kilobytes is our average user's US object size. It might be a little bit smaller, but that's much bigger than most standard benchmarks will have. I think the standard was closer to like 2 or 3. I'm not 100% sure on that, but it was definitely bigger than the standard ones. Aerospike provides a list of benchmarks with drive names next to them. Some Aerospike generated themselves. Some are third-party, give to Aerospike, and Aerospike trusts them. It's available on their website, but if your object sizes are non-standard, your performance might differ. So run it yourself. The 2 pieces of advice I have there are run it for over 24 hours, as the documentation suggests. I say that because the performance tends to change after about 3, 4, 5, 6 hours, depending on how far you're pushing your drive. And I believe that's because of the defragmentation profiles of the NVMe devices. They kind of they get to a point where they need to do work themselves, and then they start doing it, which retracts from the performance you're able to extract out of the NVMe device. Someone from Micron or Intel can correct me if I'm wrong on that. Lastly, run it on multiple drives at the same time. Just because one device performs well on a system doesn't necessarily mean when you throw 8 of them into the same piece of hardware that it will work in the same manner. You might have kind of weird interactions between the devices running together, limiting throughput. Okay, so the conclusion we came to was that we were going to use some 3.2 terabyte NVMe drives. The big goal here was to match the specs of our previous cluster. So we had 18 nodes in our old cluster using 1.2 terabyte SSD drives. That gave us a total of just around 300 terabytes of usable storage. Our new cluster ended up with 307 terabytes, which is pretty close. RAM was also pretty matched, so 12 nodes sounded pretty good to us. We started looking through this process, and we realized there were a couple things that wouldn't work with the standard, like add a node, remove a node mentality. So the process is typically add all your new nodes, and then drop one by one the old nodes, wait for migrations to complete in between each one, and move on with life. There are a couple things. One, migrations take, I don't know, somewhere between 1 and 6 hours, depending on how aggressively you push it. Other thing is when you're improving your density, so you're reducing the number of nodes you have, the amount of storage that you have on your new nodes is significantly higher than the amount you have on your old nodes. So as this kind of flowchart is removing the old SSD nodes, kind of going down in the second column, once we get down to drive number 2, we have suddenly required more storage per node than what's available on the actual nodes. This is a problem. There are ways to get around it by tuning your config, I guess, but it wasn't pretty, I'll put it that way. Reached out to Aerospike support. They provided us with a pretty awesome way to solve this problem, and it involved the rack awareness feature. Basically, what you do is you create all of your new nodes as their own rack, and all of your old nodes sit in your old rack, and you have all your new nodes and old nodes together, rack ID 1, rack ID 0, you drop your old rack. You have at least one copy, hopefully, of your data sitting on your new rack, and your new rack will just start replicating to itself. You have a few minutes of, yeah, he helped me out with that, I think.
There's been a better way now with the VSM.
Hey, I'll talk to you later. Cool. So this was the way we did it at this point in time. You have a few minutes where you only have one copy of all of your data on the cluster, but once your migration's complete, you're pretty all set. The results of this were our writes, the percent of writes that took greater than 1 millisecond, which is kind of how Aerospike does its metrics, went from 20% to 5%. So that's a pretty significant improvement in writes that are taking 1 millisecond. And we also ended up spending the exact same, almost exactly the same amount per node as we did with the SSDs. We have, instead of 18 nodes, 12 nodes. So we had a cost savings with a performance improvement. And that's something I love. Cool. Lastly, this last scenario is about read hotkeys. Well, I'll first talk about what a write hotkey is. A write hotkey is when you are trying to do a write on a specific key more frequently than your actual storage can keep up with. This happens if you hopefully not too often, but it can definitely happen. Aerospike will throw an exception on your client side when you exceed whatever the threshold is. I think it's 20 at the same time by default. Read hotkeys are kind of the same idea where you're trying to extract the same key over and over and over again from the namespace, but there isn't really a queue or anything along those lines. So basically, you'll saturate your drive performance, or you'll saturate your performance without really thinking too hard about it. And so this is kind of the story of how that happened. So this is a Prometheus graph of disk I/O. One morning, I get an alert saying that we are kind of having write transaction failures and read transaction failures weirdly. And after digging in a little bit, I found this one specific drive out of all the other drives in this cluster is misbehaving. So I thought bad drive. So I dropped the node from the cluster, and suddenly I see another drive in a completely different node kick up. And so this got me thinking a little bit, what's going on here? I reached out to Aerospike support. I was like, maybe like some partition imbalance, I don't know. And they put me in the direction of debugging read hotkeys, which at this point I had never really heard of before. The recommendation for this is, A, it's hard. B, you have to enable debug logging. I think there are probably other ways maybe to dive into it, but you have to enable debug logging on all read and write transactions. Now, if you're doing 100K read and write transactions a second, that's a lot of log lines. So there should be like an asterisk in this slide saying, run this with care, because you'll suddenly have that many log lines in your log. The one kind of saving grace, maybe, is that if you're using systemd or journald, it has rate limiting built into it. So you end up with, I think it's 5,000 log lines every 30 seconds being written out. So if you want to actually see what's happening, you have to reconfigure that. So if we run a sort and a unique on here, we can see that this key at the bottom had 421 reads as opposed to, or I should say this digest at the bottom has 421 reads compared to all the rest, which had, I don't know, small amounts that really don't matter. So that's our problem child right here. So what is this? Digests kind of are, I don't know, digests are a ripe MD160 hash. So basically it's a hash of your namespace name plus your set name plus your key name, I think. And it's a one-way hash, so you can't reverse it easily. So you have to go and figure out what this is. You can do reads based off of this key. So you can say, this digest. You can say, give me the data that's at this digest. And you can try to figure it out based off of what the data is at that point. You can look at your application logs. Maybe you can crank up some verbosity and make it print out every time it does a write on here on this specific digest what the key was associated with that. We happened to come across this log line sitting amongst many other on our Espresso servers. And the key thing here is the IP main underscore. So IP main underscore, this is how we represent the key for our hashed IPs, and they all start with IP main followed by an MD5 sum. After a bit of debugging with the developers, they were able to track down a piece of code. I'm not sure it was exactly a string null, but like it was the equivalent of it. So we were doing reads on IP main underscore over and over and over again. So application bug, but we still have this problem on our hands until the developers can fix this piece of code. They turned around a release in probably about, 2-3 days minimum, something like that. But we still had to deal with this for the time being. Aerospike support, again, gave me the awesome suggestion of enabling read page caching, which enables the Linux kernel read cache as a way to get around this. So what this does is every time a read occurs, if it's frequently happening, it'll be stored in the Linux RAM that's available on the server, and hopefully instead of going to disk every time on this read, you can actually just hit your cache. Problem gone immediately, like disappeared. Everything went back to normal. This feature was added in a relatively recent version of Aerospike, so you've got to be running 4.3 at least, and enable it with care asterisks, says the documentation, because it might do weird things. But keep that in mind, and it can solve these problems. The other options are: should the client update should the client application be updated? Should this be happening? Maybe it should. Maybe not in this scenario, but in some scenarios, maybe this actually should be occurring. And so maybe you need to scale up your hardware to deal with this, or maybe some other solutions. But more IOPS equals more money. So, yeah. Anyhow, that's kind of my spiel about kind of some operational scenarios. Some takeaways I have from this: monitor everything. You never know what metrics you might actually need. If you're able to use a tool like Prometheus, which scrapes everything, that's awesome. It's much easier to look at metrics that you have that you didn't know about than it is to implement them after the fact. Alert anomalies. This one hotkey issue was one drive on one server in one cluster. It might have been more clusters, but either way, it's a very small anomaly. If you look at averages about everything, you're not going to see problems like this. Capacity plan for failure. When migrations are occurring or you have a cluster that needs to be rebuilt, your network I/O that you're using is much higher than what you can normally plan for. Make sure you consider things like that. Lastly, trust in Aerospike support. I've had hours worth of conversations with them over the years, and they will hopefully point you in the right direction at the very least. That's my deal. If you have any questions, I'm happy to answer them, and thank you. No questions? Yes? Sure. Yeah.
So when you say look for anomalies, are these guys back can't roll another
Yeah. Yeah. So the question is. Can you repeat the question you answered? Yes, sir. So the question was, when I say alert for anomalies, do I mean we had an anomaly and then we added some metrics and then we'll catch it next time? Or do we have a way of doing this? And are we also using Alert Manager, which is kind of a side-by-side with Prometheus? It's a great question, and I think it's something that it's a direction that's kind of like on my what's next. We are currently responding to like situations where it's like this happened once, so we'll catch it next time. There's a neat health check feature built into ASADM as of the last couple years, I think. It has some sort of basic anomaly detection as well. So if you want to see if there's a node that's misperforming compared to the other nodes, I think that's built in now. I don't know if that's enterprise only or not, but it's available. We'll get to it. Cool. All righty. Well, thank you.